Now that we've defined inner products, we are going to focus on vectors that are orthogonal to each other in whatever arbitrary vector space we're talking about. If we know that vectors are orthogonal, that usually makes them a lot easier to work with. So first, let's consider a collection of vectors, v1 through vn. If every vector in the collection is orthogonal to every other vector in the collection, we will say that we have an orthogonal set of vectors. Sometimes people say this as the vectors are pairwise orthogonal, meaning that if we pick out any two vectors at random, as long as they are different vectors, they are orthogonal to each other. So, as an example, let's look at the vector space C from minus pi to pi that we talked about in the examples videos of the last section. Remember here we have an inner product. Inner product of two functions is, well, we had this factor of 1 over pi just to make things turn out to be unit, and it was the integral from negative pi to pi of the product of the two functions. And in the exercises, and we're not going to go through all the details here, the functions cosine of mx and sine of nx for integers m and n, these are orthogonal to each other. What we didn't show, however, is that if we have two different cosines, so cosine of x versus cosine of 2x, or something like that, as long as we have different integers here, those will also still be orthogonal to each other, and the same thing is true for the sines. So if we take a set where we have all the sines, sine of x, sine of 2x, sine of 3x, and so on. And I'm just going to put the cosines as a separate set, but put a union here. I'm really just making a set of all of these. So I have cosine of x, cosine of 2x, cosine of 3x, and so on. Now, we're specifically here using positive integers. If we put negative integers in there, well, cosine of negative x is the same thing as cosine of x, so it would be a repeat vector. And sine of negative x is negative sine of x, so that wouldn't be linear independent. It's actually just a multiple of sine of x. So we need, as long as we're just looking at the positive integers, and I'm not going to talk about what we're going to do if the integer is 0. That can be included, but we have to do something slightly different here. But the point here is that all of these vectors are orthogonal to every other function. And so this collection of vectors is an orthogonal set in C of negative pi to pi. And it's actually an infinite orthogonal set. That's not usually possible. We'll mention a little bit why that's true a little bit later. They define the orthogonal set as a finite collection of vectors. But here we actually have an infinite collection, and that's perfectly okay. We can do that. Now we can go one step further. Since we showed that all the sines and cosines have norm 1, that was part of the exercise that we did, we can actually say we have an orthonormal set. An orthonormal set is simply a collection of vectors, an orthogonal collection of vectors that is all unit vectors. If they're all unit vectors, then they're called orthonormal. Another way of looking at orthonormal sets is that if you take the inner product of two vectors from the set, so if these u's here are supposed to be orthogonal, and we take the inner product of ui with uj, then we will get 1 if I equals j, if we're dealing with the same vector. because that vector is supposed to be a unit vector and the inner product is the square of its magnitude. Or that inner product will be 0 if they're different, because they're supposed to be orthogonal. This is frequently written with this delta ij notation. This actually has a name that the book doesn't tell you, but it's the Kronecker delta. And we won't be using a lot here, but it is a common shorthand in parts of mathematics and especially in physics as a way of denoting when two numbers are the same or different. So if we put the same number in both slots, we get 1. If we put different numbers, we get 0. So not a lot really to say there, other than the fact that we're using it as a way to talk about our orthonormal set and their inner products. Now, what makes these so useful? Why do we care so much about sets of orthonormal or orthogonal vectors? Well, if we have an orthogonal set of non-zero vectors, specifically non-zero here, technically that was part of our definition of orthogonal set, but 0 is orthogonal to everything. But here we specifically need to leave out 0. If we have an orthogonal set of non-zero vectors in an inner product space, then those vectors are automatically linear independent. This is pretty easy to prove. All we need to really do is set up our linear combination of these vectors. So we set that linear combination up to equal 0. We're trying to show that means all the coefficients have to be 0 because of linear independence. We're going to take the inner product of this, of both sides, with the vector v1. So just put the same thing in here. Yep, v1, not c1. Technically here we had the 0 vector, we had to take its inner product with the v1, but of course the 0 vector inner product with any other vector just gives the number 0. Now how does this help? Well, we can break this apart. We have a linear combination in an inner product. We can split this up as c1 v1 v1 plus c2 v2 v1, and so on and so forth until we get to cn vn v1. But the important part is that these are orthogonal. v1 is specifically orthogonal to everything other than itself, all the other v's. So that means v2 v1 has to be 0. vn v1 has to be 0. The only thing that's not automatically 0 on this side is this first one. So c1 times v1 v1 has to equal 0 because it's the only thing left on that side. But what is the inner product of v1 with itself? That's the same thing as the magnitude, or the norm, of v1 squared. And we're assuming here that v1 is not 0. That's one of our assumptions. That means its norm cannot be 0. So we could just divide that out. This immediately shows c1 has to be 0. So we showed that one of our coefficients has to be 0. What about the other ones? Well, the only reason we got c1 specifically is because we used v1. If we want to get c2, we'll just take the inner product with c2. The inner product with v2. So then we replace all these v1s with v2s. The only thing that would survive is the c2 times the norm squared of v2. And we do the same thing. We just have to do this with every single one of the vectors, v1 through vn, and we get that every coefficient is equal to 0. And if all the coefficients are equal to 0, if we can force that, then that shows that these vectors have to be linear independent. Kind of an interesting consequence of that we can already even see if we look back at our c from negative pi to pi. I mentioned that these function spaces, that these collections of continuous functions on intervals, are not finite dimensional. And what we've basically done is we've found an infinite set of vectors that is linear independent. No matter how many vectors you take from this collection, and you take their linear combination set equals the 0 function, those coefficients always have to equal 0. So we basically have a proof here that these function spaces are not finite dimensional. So a little bit tricky to prove that directly, but once we actually have all this inner product stuff, it actually turns out to be not too bad, as long as we can take some integrals. But speaking of which, let's actually talk about bases that are orthogonal sets. Because if orthogonal vectors are orthogonal sets of vectors are easy to work with, what about bases that already have that condition? Or even more specifically, let's look at orthonormal bases for our vector spaces. Because then we can even just say that they're all unit length, sort of like our standard basis in Rn. In the standard basis in Rn, those are always orthogonal unit vectors. So we're kind of regaining some of that idea in this arbitrary vector space. And so once we start looking at orthonormal bases, we actually get some results pretty quickly. So our first result is if we have an orthonormal basis u1 through un for our vector space V, if a vector V is written in terms of those vectors, so what we're saying here is that the coordinates of V are C1 through Cn, then all these C's can be found by just taking the inner product with V with each of the UIs. So if we write this out, so what do we have? We have the coordinates. I'm going to go ahead and call this basis E, just to give it a name. The coordinates of V in that is the vector C1 through Cn, but these coordinates are just the inner product of V with U1 through the inner product of V with UN. We can just use that inner product to immediately get us our coordinates. We don't have to solve. We just have it. And that's a very useful thing to be able to do. Now again, we can prove this. If we just set up our V as this sum, I'm going to write it out without the summation notation. Oops, that should be a C. We're going to take the inner product of this with UI. So V comma UI. Then we have, well, all this again. Oops. We need this to have a UI in it. Just like before, we can actually break this up. This is C times the inner product of U1 with UI. Through Cn, the inner product of UN, UI. And just like before, because UI is orthogonal to everything that's not UI, all the other ones, then all those other terms go away. We're just going to be left with the ith one, Ci times the inner product of UI with itself. But of course, the inner product of UI with itself is is the square of its magnitude, or the square of its norm. And we're insisting here we have an orthonormal basis, so each of the vectors has norm 1. So this is really just Ci. So Ci is this inner product. Easy enough. But it means that once we have an orthonormal basis, once we have this very nice situation, we can find the coordinates of any vector just by taking the inner products. And we don't have to do anything more than that. We get some nice other results from this. We can use this to simplify not only coordinates but also the inner product itself and the norm. So here, if we have our orthonormal basis, we have two vectors with coordinates. U has coordinates ai, v has coordinates of the i's, and we can take the inner product of u and v by just multiplying the corresponding a and b, and then adding them all up. This is, in fact, exactly the same as format as the scalar product that we were using in Rn. So, in fact, if we can write this out in coordinates, we can say the coordinate. Remember the coordinate vector of u, coordinate vector of u. And again, I'm going to call this e. This is the column vector a1 through an. And then the coordinate vector of v is b1 through bn. What is the scalar product of these two vectors? Well, it's this column. Well, we turn this into a row times this column, and we just end up with this exact same formula. So really, this, once we're working with an orthonormal basis, the inner product is given as the scalar product in the corresponding Rn of the coordinate vectors. Again, there is a proof to this in the book. It's very similar to the last two proofs, but I'm going to leave it to you to either try it yourself or to look up in the book. It's really not too hard to show. What about the norm? Well, this one, we have exactly the same thing. We have that the norm can be written in the norm squared here is just a sum of the squares of the coordinates, just like we had in our standard basis. You can say here that the norm of v squared is just actually, let's even take out the square. The norm of v is literally just the norm of the coordinate vector of v. It's the magnitude of that. And here we don't even have to go and really use the orthonormal property to actually derive this. We can actually use the previous corollary. So here, what is the norm of v squared? Well, it's just the inner product of v with itself. Well, we know what the inner product of v with itself is. It's literally, from this formula, just take the coordinates of v, multiply them to themselves. So we have c1 times c1, so c1 squared. Then c2 times c2, so we have c2 squared, and so on and so forth. So, just using the same form that we had up there. So, really, this is just a version of the previous one. Alright. Now, since my videos have been getting a little bit on the long side recently, and the next topic is going to be a little bit different from what we've been doing in this video, I'm going to go ahead and split this video up, and in the next video, we're going to take a detour from these arbitrary vector spaces, these arbitrary inner product spaces, and we're going to actually talk about matrices. So, I'll see you then.